Hello everyone, today let's take a look at QP123. We're looking at the geometric distribution here, finding the expected value and variance. We can do this in two main ways. The first way just by using basically the definition of expected value and variance, and the second way we're going to look at using the tail sum formula, which we just talked about in QP122. Okay, so x is a geometric random variable, so it basically models the wait time until the first success, where success happens with probability p. So for instance, if p equals 0.6, that means that on any one of my given trials, I have a 60% probability of success. Well, then the probability that x is equal to 4 is basically going to be interpreted as the probability that I have to do 4 different trials in order to get my first success. So that means on my first trial, I get a failure. In this case, that would happen with 40% probability because our probability of success is 0.6. So the 40% on the first trial, then 40% chance of failure on the second trial, and 40% chance of failure on the third trial. And then on my fourth trial, I get a success. So that's the probability that x is equal to 4. I can do that because we're implying that all of these events are independent because they're all Bernoulli. I didn't write that up here, but it's implied. So definition of expected value, we sum over all the possible values that x can take, which is going to be 1 to infinity because it could take any number of trials to get our first success. So I take the sum over all possible values that x can take of x times the probability of that exact number of trials being the one that gives us our first success. And this probability here is going to be represented by this PMF, so I'm just going to go ahead and plug that in. So p times 1 minus p to the power of x minus 1. In this case, my iterator's x here, but up here it's k. This right here means I get x minus 1 failures in a row, and then on the last one, I get a success, just like we modeled here. Okay, so now we can actually evaluate this infinite sum. First of all, I can pull out this constant p like so, and we're going to get this. Now this term right here looks awfully similar to the one from the geometric series formula, which we talked about in QP64. We proved in QP64 that this right here was equal to 1 over 1 minus r when r is less than 1. So now if we know this formula, we want to get these to look like each other so that we can express this infinite sum as some term like this. So there are a few differences. The first one is that here our iterators starting at 0 and here our iterators starting at 1, but you notice that x equals 1 to infinity of this sum is just going to be the same as x equals 0 to infinity of that sum, because when we plug in x equals 0, our first term will just be 0, so they're going to be equivalent. The other obvious difference is that we're multiplying by our iterator out in front here, but we're not here. Also, this one is to the power of our iterator minus 1, while this one is just to the power of our iterators. And also one more thing, this formula here is only true when the absolute value of r is less than 1. In our case, we're saying that r is basically this 1 minus p term. So 1 minus p is a probability, so it's always less than or equal to 1. The only case where it actually equals 1 is when our probability of failure is going to be 100%. So if r actually does equal 1, well then this series right here will diverge. So if 1 minus p equals 1, well then the probability of failure is 100%. So we would actually expect this series to diverge as well. That's just because if the probability of failure is 100%, then the probability of success is 0%. So the expected waiting time until the first success is obviously going to be infinity because it will never happen. It has a 0% probability. We can just write that as a minor asterisk, right? If p actually equals 0, the probability of success is 0, then 1 minus p is equal to 1. And then the expected value of x is just going to be infinity, or it's going to diverge. Now, assuming that 1 minus p is actually less than 1, now let's figure out a way to solve this. Well, in relation to this formula over here, the only difference over here just basically looks like we took a derivative of this side, right? So that's a good place to start. I'm going to rearrange this equation to give me a new formula such that I take the derivative of both sides here. So when I take the derivative with respect to r of this left-hand side of my equation, well, I'm going to get the sum from k equals 0 to infinity of k times r to the power of k minus 1. On the right-hand side, what's the derivative with respect to r? Well, I can do low d high, so 0 minus high d low. So in that case, it's going to be negative 1 all over low squared, which is going to be 1 minus r squared. So when we took the derivative of both sides of this formula, we got to this relation down here. You can see that this side looks very similar to what we have up here. This is also going to be 1. So now we can use this and just plug in 1 minus p where we see an r on this side. Okay, sorry for all the circling. For this term right here, we plug in 1 minus p right here. We get 1 over 1 minus 1 minus p in parentheses all squared. And when you simplify on the inside, you distribute the negative. Obviously, this is going to cancel to just p on the inside. So we're going to have 1 over p squared for this term right here. Now we also had this p out front, which was our constant. So we still have to multiply this by p to get our expected value. The expected value of x is just p on p squared, also known as 1 on p. So pretty simple right there. Okay, so now if we wanted to calculate the variance straight up using similar methods, well, let's do that down here. So the variance of x. Okay, we showed in QP92 that this is just equal to the expected value of x squared minus the expected value of x all squared. Now, obviously, we just calculated the expected value of x right here, so we can just plug that in. When we do so, we get 1 on p squared for this term, and now we just need to calculate the second moment of x. Now, here's the definition of expected value. The expected value of x squared is the sum over all the possible values that x can take of x squared times the probability of that value occurring. We know that this is our p math for the geometric. Okay, so now we literally can use the exact same strat that we did to calculate the expected value of x. First first of all, I can just pull out my constant because it's constant with respect to my iterator. Okay, now this part might get a little bit messy, but this looks an awful lot right here like the second derivative up here. So we're again going to take the second derivative of both sides and see what happens. So I start with the infinite geometric series formula that I know from QP64, and now I can take basically the second derivative of both sides with respect to r. Let's do that. Okay, let's take the second derivative of both sides of this equation right here. When I do that, I'm going to start the left side. Let's take the second derivative of it. I'm going to get the sum from k equals 0 to infinity of k times k minus 1 times r to the power of k minus 2. Right, so now let's take the second derivative of this term here, which is just going to be the first derivative of this term. When I do so, a low quotient rule action, low d high minus high d low, so it's just going to be 2 times 1 minus r over 1 minus r all squared, so just 1 minus r to the power of 4. Now a little cancellation right here, we're going to get 2 on 1 minus r cubed. Okay, so by differentiating this twice, we're going to get this equivalence right here. These are equal, and that's going to help us solve right here. All right, so I made a little bit of new room action, but this is what we just showed right here just by taking the second derivative of the geometric series formula. Now this is what we're actually trying to solve for, so we want to make it look like this over here so we can use this. So good thing to know when you're trying to relate x squared to these like kind of factorial-like terms, basically what you can do is you know that x squared is just going to be equal to x times x minus 1 and then plus x. I feel like this has come up quite a bit in all the proofs that we've done, so it's a good thing to know. If we write x squared like that, well then this is going to be equal to p times the sum from k equals 1 to infinity of x squared, but we're replacing it with this right here, so it's going to be x times x minus 1 to 1 minus p to the power of x minus 1, and then we can take this x to another sum. So this term up here is equal to the sum of these two terms down here, and you'll notice that this one right here, we just did that when we were taking the expected value. We know that this is just going to be equal to 1 on p. Okay, now this term looks very similar to what we have over here, so one more thing to do, we need to get this -2 to line up with this one. So to do that, I can just multiply both sides of this equation by r, and then this will turn into a k minus 1 right here, and then on this side I'm going to multiply by r. Now we're all set. This sum right here looks exactly like the one over here, so now we can just plug in 1 minus p for r over here. When I plug in 1 minus p for r, I get this equation down here. Now this is going to simplify in here to just be p, so I have 2 on p cubed times 1 minus p. So that's what the sum in orange right here looks like, so now we need to multiply that term by p. When I do that, one of these is going to cancel on the bottom, so over p squared, and then we still need to add on our 1 over p, so plus 1 on p. Sorry for all the algebra, maybe I do too much algebra, but basically what we can do here is multiply top and bottom by p to get a common denominator. When I do that, I'm going to get p on p squared for this term. Now when I add these up, I get 2 minus 2p plus p, so this is just going to be 2 minus p all over p squared. Okay, so this right here is the second moment of x, the expected value of x squared. Now to get the variance, we just still need to subtract off this 1 over p squared term. So when I do that, it's going to be pretty simple. I'm going to do 1 minus 1 on p squared. It's going to equal 1 minus p on p squared, which is going to be our variance. Now actually a much easier way to get the expected value and variance, especially the expected value, is just to use the tail sum formula. So we showed that in QP122, if x is a random variable that takes values in the non-negative integers like it does here, well then the expected value of x, we can express that as a sum from m equals 0 to infinity of the probability that x is greater than m. Now in our case for the geometric, what is the probability that x is greater than m? Let's start with some specific values. So what's the probability that x is greater than 0? Well, the geometric's counting the number of trials until the first success, so we have to have at least one trial. So the probability that we have more than 0 trials is just going to be 100%. So now what's the probability that x is greater than 1? Well, in order for the number of trials until the first success to be greater than 1, we have to have at least one failure. So this is just going to be equal to 1 minus p, the probability of a failure. Now the probability that x is greater than 2 represents the probability that we have at least 2 failures before our first success. So that's just going to be equal to the probability that we have 2 failures to start, which is just going to be 1 minus p squared. Now you can see the pattern. So the probability that the number of trials until the first success is greater than some value m is just going to be equal to 1 minus p to the power of m, because we need at least m failures to happen before our first success. And so we can just substitute that in right here. And now you can see how much easier this is going to be. We can just directly apply the geometric series formula for an infinite sum. It's just going to be 1 over 1 minus p, which is just equal to 1 over p. That's the power of the tail sum formula right there. So now let's go ahead and calculate the variance of x. Okay, now the variance of x is also going to be a little bit easier to calculate using the tail sum formula. So first of all, the definition of variance is going to be the expected value of x squared minus the expected value of x all squared. We already know the expected value of x. It's going to be 1 on p. We just showed showed that. So right here we're subtracting a 1 on p squared from the second moment of x. So now we just need to calculate this. So definition of the expected value of x squared right here. In the first part we calculated this straight up, but using the tail sum formula, again, it's going to be a little bit easier. But you can't directly apply the tail sum to this because we have an x squared, but you can use the exact same idea. So just like we did in QP 122, if we're taking this sum right here, well, what are we doing? Well, first of all, x being 0 doesn't matter, so we could just essentially start that at x equals to 1, as we can always do because our first term is going to be 0 here. So now I have some probability mass that x is equal to 1, and on my first pass through this loop, I'm going to take that probability and multiply it by 1 squared. So I want to count this one time. Now on my second pass through the loop, I'm going to take this probability mass and I want to count this one 2 squared different times, right? So 4 different times. Now on my third pass through the loop, x is going to be equal to 3. So the probability that x is equal to 3 is represented by this mass right here. And I want to multiply that by 3 squared. So I want to count this one 9 times. Similarly, I want to count this one 16 times, and etc. Now with tail sum, the idea from QP 122 is that basically what we're going to do instead of that is that on our first pass through the loop, we're going to sum up all of these probability masses one time and going on to infinity too with all the greater values of x. Now when we get to our second pass through the loop, again, this is going to make sense if you watch QP 122, we're basically going to be right here and we want to count this value 3 more times because we already counted it once when we were taking the probability that x is greater than 0. So now we want to count this 3 different times on our second pass through the loop, which means we're going to count all of these 3 different times. I'm going to count this one 3 different times, etc. So now I've correctly counted this one time and this one 4 times. So now when I take the probability that x is greater than 2, I'm going to be over here and I want to end up counting this 9 times, although I've already counted it 4 times. So I need to count it 5 more times. So I'm going to end up counting every single one of my future elements 5 more times as well. So 5 times, and then this one will be counted 9 times. Okay, so now for the probability that x is greater than 3, we've currently counted this mass right here. We've counted it 3 times plus 5 times plus 1 time on our initial. So 3 plus 5 plus 1, that's going to be 9. We've counted this one 9 different times. So we still need to count this one 7 more times. So now when I take the probability that x is greater than 3, I'm going to count everything 7 different times into the future. So what's the pattern? Well, first I added everything 1 time, then I added everything 3 times, then I added everything 5 times, and now I've added everything 7 times, so all the odd numbers. So all this tells me is that instead of calculating it like this, basically what we can do is take 1 times the probability that x is greater than 0. That's the first thing we did with this pink color. Now I add on, we added 3, right? 3 times the probability that x is greater than 1. Now I add on, well, what was it? 5 times the probability that x is greater than 2, plus 7 times the probability that x is greater than 3. Then this is going to keep on going with our coefficients being the odd numbers. So basically I can encode this in a formula as the sum of j equals 1 to infinity. Then I need to encode my odd numbers, so I'm going to take the sum over 2j minus 1. These are going to represent my odd numbers because when I plug in 1 here, I get 1. When I plug in 2, I get 3. When I plug in 3, I get 5, etc. Then we multiply that by the probability that x is greater than j minus 1, which are all these terms, because when j is 1, we want x greater than 0, which we're going to get. Okay, and now we can solve this. Well, the probability that x is greater than j minus 1, if we plug in j minus 1 to this formula that we found over here, well, then we're just going to get 1 minus p to the power of j minus 1 here. Now I can just distribute what's inside of here. So when I do that, I'm going to have 2 different sums now. So I'm going to subtract off the sum from j equals 1 to infinity of, on this side, it's just going to be 1 minus p to the power of j minus 1. Now if we let k equal j minus 1, well then we can do this, and then we have to replace our iterator like this. This looks exactly like the geometric series formula, which is going to be 1 on 1 minus 1 on p. So it's just going to be 1 on p. So we're subtracting off 1 on p here, and then we can pull a constant out from this first term. I've already calculated this a million times at this point. It's just going to take the derivative of the geometric series formula on both sides, and then we're going to get 1 on p here, and then we need to multiply that by 2. Right? Actually, it's 1 on p squared. Then I can make this just p on p squared. Then when I take this, I'm just going to get 2 minus p on p squared. So that's the expected value of x squared, our second moment. You can see if you know the tail sum formula, it's going to be a little bit easier. We didn't have to take any second derivatives. And again, one more time to get the variance, all you have to do is take this, what we just found right here, and subtract off the expected value of x all squared, which is going to be 1 on p squared. And when you do that, you find that the variance of x is just going to be equal to 1 minus p on a p squared. Also down here, one more time, we figured out that we were multiplying all of these by the odd numbers just by looking at the general pattern. But how do you actually show that this formula holds true? Well, what we were saying down here essentially is that x squared is just equal to the sum of all the odd numbers under it. So the pattern that we found is that the sum from j equals 1 to x basically of 2j minus 1 is equal to x squared. So how do we actually show that that's true? Well, QP65 series summation formula, this is going to be equal to 2 times the sum from j equals 1 to x of j minus the sum from j equals 1 to x of 1. Well, this term over here is obviously just going to be x, and then we know from QP65 that if we take the sum over the first x natural numbers, well, we're going to get basically x times x plus 1 divided by 2. So if I replace this with that, well, then we're going to get a cancellation of the 2 here because we're multiplying by 2, obviously, so they're going to cancel right here, and then we're just going to get x times x plus 1 minus x, which is just going to be equal to x squared. That was just kind of a proof of the pattern that we were taking for granted in this formula earlier. I thought it'd be more rigorous, but now basically you can see that the tail sum formula is just going to make life a little bit easier if you know how to think about it as this kind of horizontal summation instead of like individual vertical summation.